So I think what we start off as a common theme about climate change is the change in our atmosphere, rise in CO2, and it has two effects. It's warming the planet, and the CO2 dissolving in the ocean is lowering the pH and saturation state. And so when you look at these changes in the atmospheric composition and what their impact on climate is and project that in coupled ocean-atmosphere circulation models, you see projections of what aragonite saturation levels or the carbonate chemistry is going to be at various points in the next century, depending on particular emissions scenarios that Ove went over the other day. But the real question is, when you look at these global or regional pictures of water chemistry or temperature, what does it look like on the scale of the reef itself, and are these things changing on the scale of the reef? The answer is yes, and the question is, how do we understand how those changes take place and what's driving them? So we know there's been a lot of different studies trying to look at the natural variability in carbonate chemistry on reefs, and you have different kind of CO2 extremes. The lows can be less than the last glacial maximum. The highs can be much higher than even the business as usual scenario at the year 2100. But the question is, we need some sort of context to understand when people measure these changes in a particular reef environment at a particular time, what does that mean for reefs more broadly? That is, how can we extrapolate our observations at a certain point in space and time to reefs in a more general way? And that depends a lot on the physical context of the reef environment. And so just to kind of go over the general concept here is that changes in water chemistry that occur on a reef, and this is particularly important in shallow reefs and very important in nearshore shallow reefs, is that water is flowing over a shallow reef. The community will take up a DIC and alkalinity according to calcification at production. They'll release DIC at night according to respiration. There'll be a lot of different other kind of fluxes, nutrient uptake, release, PON uptake and release. But the important thing to know is that the relationship between the physics, the chemistry, and the metabolism is that when you have water flowing over the reef, it flows really fast. You get an uptake to the benthos, you get a reduction in the concentration. But more importantly, if I reduce the cross-reef transport, then the changes in concentration increase. And so in this case, we're going from a concentration which is about a 28-point font to a concentration which is now about a 14-point font. So there's a fundamental relationship between the change in concentration you see over a given distance to the flux and the cross-reef transport. And the cross-reef transport in a lot of these shallow reef systems, a majority of them, is driven by waves. So what happens here is this is basically a kind of two cartoons. This is a sideways view of a reef platform with a lagoon, and this is a kind of a aerial view or downward-looking view of a reef platform. What happens is waves come into the reef, they break on the forereef and on the reef crest, and that actually pushes the water level up. And when the reefs do that, they push the water level up, the water flows over the reef and then into the lagoon and then back out through the channels. So this is what it looks like. This kind of wave-driven circulation is a very common feature across the Indo-Pacific, the Caribbean, et cetera. So you have waves pushing the water level up, driving flow across the reef, into the lagoon, and back out the lagoon. And so in order to really understand how changes in chemistry or even temperature are going to occur on reefs, you really have to start with understanding the physics of wave-driven circulation on reefs. So what does that look like? Well, this is kind of a simplification of a wave setup model that Gourlay came up with based on conservation of incident wave power. And don't worry too much about all the stuff in front. The important thing is this relationship down here. And so it consists of two things. How much the water level sets up at the reef crest, which is driving all of this circulation, is a function of the incident wave power. So you have bigger waves coming in, you're going to drive higher wave setup, and you're going to drive stronger circulation. And then, of course, it's inversely proportional to the depth of the reef crest. Shallower reefs will break wave energy faster, and that'll drive higher levels of wave setup. And so what happens is you can take these concepts of the relationship between changes in chemistry, fluxes, and transport here over in the reaction, and then you can mix them with wave-driven models of setup and circulation, and you apply some simplifying assumptions to make it a bit manageable. And then you come up with something along here in the bottom, which I agree it looks a little bit cumbersome still, even though I've actually I've made a lot of simplifying assumptions. But the important thing is if you just bear with me, I can actually explain this in really simple terms. It comes down to three real factors. So what you can do is you can group all those variables into compound variables. And what you can do is you can start with the first one, which is a ratio of metabolism to wave forcing. So this J prime term here, you see this flux to wave height in the square root of wave period. What that means is if you have a higher flux, you're going to get bigger changes in chemistry. That part should be obvious. But also, it's inversely proportional to wave power, because if you have more waves or bigger waves coming in incident to the reef, you're going to drive stronger circulation. The water is going to have less time to react with the reef, so you're going to get less changes in concentration. Then the next part is a reef geometry factor, which has to do with the barrier reef separating the lagoon and the ocean. And there's two factors here. One is the length of the reef, that is the distance from the crest of the reef to the back reef. And so as you make that distance longer, you give more time for the water to react, but you're also weakening the pressure gradient across that reef crest, across that reef flat. And so that actually slows down the transport, which again increases the changes in concentration. And then you also have inversely proportional to the reef crest for a number of reasons, because that affects wave setup, but also because when you have a shallower water column, you're going to get a stronger signal. That is, the changes in chemistry are going to be stronger because you're dividing the flux effects over a smaller water column. And then finally, this is a little bit more cumbersome, but this represents the frictional resistance of the system. And this has two components. It's a frictional roughness of the reef. That is, a smooth reef will have very little friction under a certain pressure gradient, and a very rough reef will have a lot of friction generated, so it'll slow down the flow. So the more friction you have on the reef flat and in the channel, the slower the water is going to move through the system, the greater the changes in chemistry are going to be for a certain flux. And so that's kind of a very simplified, one-dimensional analytical approach. And that the advantage of doing that is it allows you to get right at the functional relationship between all the morphological variables, the offshore hydrodynamic variables, and the metabolic variables to see how those influence the changes in concentration that you see. But what you'd want to do, because of all the simplifying assumptions that go into that, what you want to do is actually test this in a more of a truly three-dimensional sense. And so you want to ask the question of, like, what is a typical reef going to see in terms of changes in carbonate chemistry? And given the amount of work that's been done in terms of measurements of reef metabolism and reef morphology and reef hydrodynamics over the past 40 years, we actually have a lot of data that which we can actually look at what the central tendency of an archetypal reef would be. And what you start with is groups of metabolism. These are production, respiration, P-to-R ratios, net calcification. And this is basically a standard reef or barrier reef flat. And then flow and morphology, these, if you go through the literature, these are kind of the standard morphological and wave climate variables that you see. And this includes the significant offshore wave height, cross-reef current, cross-reef transport, reef flat depth, the length of the reef flat, the width of the reef flat, which is in the longshore direction, and the depth and the width of the channel. So what you can do is you not only can construct an archetypal reef, but what you want to do is explore how changes in those parameters based upon the natural variation in these characteristics across various different reefs would affect the changes in chemistry you would see. Now, it's actually really hard to do this with real reef systems like you would experimentally, like in putting coral in an aquaria, because it's really hard to get permission from government agencies to say, yeah, I'd like to dynamite a really big channel in the middle and see what it's going to do to my equations. They don't like that. But what you can do is you can actually go into a numerical domain, which we've had a lot of success using numerical hydrodynamic models to predict circulation. And then what we can do is we can create numerical reefs that look a lot like this. And this is what an archetypal reef would look like. And so what you have here is this is a cross-shore direction, this is a long-shore direction, and this is basically depth. Here it's going deep, coming up the forereef. Here's a reef flat, here the channel is in between, and this is a lagoon. And then what you can do is you can put in some waves, and the waves will transform according to known wave action equations. And they'll come across the reef here, and you can see there's a lot of wave energy out here. The sun comes through the channel, and then most of it breaks on the reef. And that actually drives all this setup, and that setup in turn drives these two-dimensional circulation cells. Now, the thing about this model is it doesn't know what those analytical solutions are. What it's doing is using fundamental equations to governing momentum transport and wave transformation, and it's just plugging away and calculating the changes in those properties from one cell to the next and from one time step to the next. And so this is an example of what you do if you put in typical rates of benthic metabolism. You can generate models of diurnal changes in PCO2. And so delta PCO2 means this is the change in the partial pressure of CO2 relative to offshore. And you can see that obviously the diurnal cycles that during the day you get uptake of carbon from net photosynthesis that drives the change in PCO2 down, and at night you get release of carbon dioxide, so that drives it up. And so just to show you that I'm going to focus just on carbon dioxide rather than the entire carbonate system, but if you know a little bit about carbonate chemistry from all the talks on ocean acidification, you know that elevations in CO2, like this is basically a snapshots of the model results at midday, when I should say depression in CO2 from uptake leads to an elevation in pH and an elevation in saturation state. So even though these are not the same variables in terms of what they represent of the carbonate chemistry, these have very similar diurnal patterns. They tend to track one another in either correlative or inverse ways. And so the other thing I wanted to point out is that even in a very idealized, simplified reef system, you can actually get complex diurnal behavior. And a lot of this scalloping you see, this is basically variations in delta PCO2 on the forereef, back reef, and in the lagoon. And what you see is that in the forereef you get a bit of oscillation. This is from the altered water coming out of the channels and flowing across the front of the reef. And that recirculation of altered water actually creates complex curves. And the other thing I want to point out is you notice the back reef and the lagoons aren't very different because most of the changes in chemistry are occurring over the shallow reef part. And so to better analyze this kind of data, you generate a three-dimensional model, which is actually four-dimensional because you have time as well. You want to simplify this a little bit. So what we want to do is reduce the 4 dimensions down into 2 dimensions by 1, depth integrating in the vertical axis, and 2, by considering the time dimensions in 2 components, one which is a diurnal amplitude, because we know the sun goes up and it comes down, and that causes diurnal variations in production and calcification. And then the second one, which is we're also concerned, is what is the net change after 24 hours? That is, it can go up and down with diurnal cycles, but what is the net change, and what does that mean for the ability of coral reefs to change their carbonate chemistry in a net sense over days to weeks or more? And so if you look at that parameter, you can just plot that in 2-dimensional space, and then you can just see a map of what this looks like in a coral reef. And you can see this is the diurnal amplitude, and you can see that blue is low and red is high. You can see the diurnal amplitude is very high towards the back reef and into the lagoon, and it doesn't change much in the lagoon. And the other thing, and you see a similar trend for del PCO2, which is that net change. It's a little bit more complicated because of this recirculation and interaction with an alongshore current. But the real thing to notice here is you can see the amplitude, the diurnal amplitude, is anywhere from 0 offshore to 75 microatmospheres. But in this central case, which this represents the archetypal reef in terms of morphology, wave forcing, metabolism, you don't see very big changes after 24 hours. You see something on the order of 10 microatmospheres. So one of the things we can do is to test our simple kind of analytical model, which is great because it shows us a functional relationship between the various variables, but it relies on a certain number of simplifying assumptions. We can compare it against what the numerical model is doing just based upon fundamental equations of momentum transport. And you can see there's generally good agreement between what the model is doing and its dependence on these 3 fundamental variables. So even though this is greatly simplifying, it's capturing a lot of the variance. And this scatter here represents our ability to use the model to explore the parameter space over a wide range of potential reef morphologies, wave forcing, and rates of benthic metabolism. The central case, being the archetypal reef, is somewhere around here at a diurnal amplitude of around 70 microatmospheres. And then what we want to do is now we have these idealized 2-dimensional, or I should say 4-dimensional numerical simulations versus a 1-dimensional simplified analytical model. How does that compare against real reefs? And so this is data from reefs where we have information on the offshore wave climate, the morphology, and rates of benthic metabolism. And you can see actually these 3 variables are actually pretty good predictors at looking at the changes in the diurnal amplitude of CO2 on a reef. And so the other thing I want to point out here, this represents the back reef environment where the changes in chemistry are the greatest. So this is what you would get in the back reef, and probably this also represents what you get in most of the lagoon. So you can see that this does a pretty good job, but the other thing I want to notice is that the central case is about 70 microatmospheres. If you look at a lot of these points, you probably say it's similar to what we get for an average from these different reef sites, maybe around 100 microatmospheres for a diurnal amplitude. And of course, when we go to the net change over 24 hours, you can actually see it's a much smaller cluster of points, and that those actually range from anywhere from -20 to about +20 microatmospheres. And again, how does this compare to real reefs? Well, it compares very similar. I mean, I admit that Bora Bay, for some reason, it's a very net autotrophic system in terms of its measured metabolic rates, but somehow it's got 0 change in PCO2. But for these other 4 reefs, you can see they cluster along the same line, the same relationship in terms of their dependence on these 3 different fundamental variables. And more importantly, you see that the net change, in this case, I averaged over a few days, not just 24 hours. You see the net change in PCO2 in water at the back reef is only about 20 microatmospheres. Now, if you consider that we're considering changes in the atmospheric CO2 of the order of like several hundred microatmospheres, these changes are actually quite small, if not trivial. So why is that the case? Well, most of what drives these diurnal changes in CO2 is actually production and respiration. And in most reefs, production and respiration are very well balanced. Most reefs are slightly autotrophic, that is, they export organic matter, which means that they're a net sink for CO2. But the problem is most reefs are also net calcifiers, and calcification is a net source of CO2. And those things tend to balance out so that you actually get reefs are neither a source or sink of CO2, at least significantly, over days to weeks. So as a summary, the change in carbonate chemistry is a function of metabolism because that's what's actually changing the chemistry, but the magnitude of those changes is equally dependent on waves and the morphology of the reef system. So this will give you the context of how you understand the changes in your environment to the particular reef you're looking at in a particular wave climate. The biggest changes are across the reef flat, even though that's not where the water spends a lot of its time. It's just because it's very shallow and those communities tend to be very active in terms of their spatial zonation and metabolism. There's a lot of diurnal complexity, so even in a very idealized 3D simulation, where you have constant wave forcing directly onto the reef and you have a fixed morphology, everything else is fixed, you can still get complex diurnal behavior because of the recirculation of altered water coming out of the channels and back over the reef. And the long-term effects, the net effects of all of this action is not very profound. So what this means is there's this kind of a limit to how much you can get in terms of a biological feedback of coral reefs changing their carbonate chemistry and creating refugia. So my impression is it's very hard for you to create refugia in these reef environments because of this balance between production and respiration. Now I will say one other comment is that when you go into systems where it's actually maybe morphologically more complex, very shallow, highly metabolically active, over longer space and time scales, the P to R ratio actually approaches more closely to 1, and that the long-term changes in carbonate chemistry are driven mainly by net calcification. But the problem then again is that net calcification is a CO2 source, so in these kind of complex, highly active, shallow reef environments, you're actually going to get a more substantial depression in saturation state. So they're going to be more like a worsening effect than a refugia. And before I want to move on, I just wanted to point out the other side of this equation, which is temperature. And this is just a forecast of what global temperature would be under kind of the business or fossil fuel intensive, the old school system before they moved to the RCP basis. And so I just wanted to mention that the changes in chemistry and the relationship between changes in chemistry, fluxes, and transport that I explained before are exactly the same for temperature. That is, instead of having a flux of DIC or TA at the benthic water interface, you have a flux of heat from downward solar radiation, net long wave radiation, sensible and latent heat fluxes across the air-sea interface. And as the water moves across the reef, it's picking up heat and the temperature increases. And so rather than look at that in an idealized sense, what we've done is focused on a reef in Ningaloo, Coral Bay, because about a couple years ago there was a very strong marine heat wave at this time. And so what we wanted to do is look at what the changes in temperature were under those conditions. And we can take offshore temperature data from satellites, and then we can look at the changes in temperature at each of these sites within Coral Bay using the same hydrodynamic model and using information on offshore wave forcing and net atmospheric heat fluxes. And so what you can do is using those tools, you can actually predict the temperature at each of these sites really well. Now the problem is the bleaching occurred in early February, and we only got our temperature sensors in mid-February. So what we'd like to know is what the thermal history was, or the thermal stress history was, leading up to that bleaching event for which we didn't actually have temperature measurements. Well, the good news is once you actually have a calibrated hydrodynamic thermal model, you can actually go back in time using time series of offshore wave climate, net atmospheric forcing, and offshore temperatures derived from satellite data to predict what those thermal histories would be. And so this is kind of a simulation of the thermal stress from the 1st of January 2011 to the end of February, so over a 2-month period. Now I know this is the same exact system, there's 2 simulations. What I'd like you to look at is a simulation on the left. This reflects what actually happened. So what happens is, in the beginning of January, you actually get an increase of thermal stress, and to the end of February, it gets up to somewhere around 20-degree heating weeks on the inner lagoon. And so using this model, we can make those projections even though we didn't have temperature data until after the 15th of February. And so the other thing I wanted to point out is this simulation on the right. At Ningaloo, under normal seasonal conditions, the temperatures hit their seasonal maximum around April. And so this marine heat wave came early, that started hitting its maximum or above its seasonal temperatures in January. So we asked the question, well, how important is timing on the accumulated thermal stress in this environment? So what we did is we imagined if that heat wave hit reaching its maximum temperatures in April. And so you can see that in this scenario, if it had come a couple months later, the accumulated degree heating waves would have been much less. And I think the last thing to note is that in this system, there was some mass bleaching, about 30% of the corals. What the amazing thing was, even though these thermal stresses were reaching 20-degree heating weeks, that most of the bleached coral had recovered within a few months. So at that point, I just want to thank my collaborators in this work that we're doing, Junlin Zhang, Ryan Lowe, and Malcolm McCulloch, and I'm happy to take any questions.